AICTE sponsored workshop. I'm really not in the field in the topic of the workshop, but my association with Professor Pandey and some other young people in recent times have shown me or indicated me that there is a lot of interesting connections between nonlinear dynamics and nanomaterials and thin films and so on and so forth. So when Professor Pandey suggested me to give me a lecture in this workshop, I thought I can bring in what I have been learning in recent times with my association with these people. So that's what I'm planning to do in this next 2 hours. So to start with, I will share my transparencies, PPTs. So let me start sharing. So are you able to see my PPTs?
Yes, sir. Yes, sir. It is visible.
Yeah,
sir.
I will go to the full screen mode. Just a moment. It will take a minute. Yeah. So I think this is okay.
Yeah, sir. Yes, sir.
Yeah. So in this workshop on energy storage, science and technology, which has been organized at Motilal Nehru National Institute of Technology at Prayagraj by Professor S.N. Pandey. So I'm planning to give my lecture on nonlinear dynamics and fractal analysis, their application to energy storage. Because after all, this is the meeting on energy storage. So whatever I have been learning in recent times and the application of nonlinear dynamics to energy storage and nanomaterials, so I would like to convey some of these ideas. Of course, Professor Pandey is an expert on this topic of energy storage in supercapacitors and fractal analysis and so on. So whatever I'm going to tell, whatever is not clear, I do hope that Professor Pandey will be able to explain further, perhaps in his tomorrow's lecture. So as you see from my title, I will be talking about 3 aspects. The basic concepts associated with nonlinear dynamics and some simple ideas on fractals and its connection with nonlinear dynamics. And then in the third part, I will try to convey some ideas of how this nonlinear dynamics and fractals are applicable to study the properties of supercapacitors, which is, I think, is a major concern of this workshop. So let me proceed. So after a brief introduction to nonlinear dynamics, essentially, I will try to introduce some very essential ideas on nonlinear dynamics, particularly on the notions of bifurcations and chaos and chaotic attractors. There is another integrable, many other interesting concepts and ideas in nonlinear dynamics, like synchronization, complex dynamical states, integrability, solitons, and so on and so forth. But in this talk, I will be essentially concentrating on bifurcations and chaos and chaotic attractors in connection with some basic nonlinear dynamical system, which I will call as nonlinear oscillator. A simple nonlinear dynamical systems, which all students of physics know about, just a linear harmonic oscillator vectored by a nonlinear force. So a simple nonlinear oscillator, which I call as dumping oscillator, and its dynamics. It's one of the simplest nonlinear dynamical system you can think of. But I will point out, I'm sure some of you already know the details of this, but this simple system cannot be solved with all the mathematical advancements during the past 400 years. You have to analyze this only numerically or through nonlinear electronic circuits and so on. But if you do that, you encounter the notion of bifurcations and ultimately complex and chaotic motion in a single scalar dynamical system. And this chaos complexity is represented by, in the phase space, by a chaotic attractor. And this attractor has some extremely interesting property called self-similarity. Self-similar structure. At every scale, you find similarity to the original one. And that is the characteristic feature of fractals, fractional dimensional objects. So I will introduce some very basic notions of fractals, fractal objects, and how you can characterize them in simplest terms. And then you find that when you go to energy storing materials, particularly supercapacitors, many people have in recent times have analyzed this surface morphology. In order to understand and utilize appropriate materials for supercapacitors, you find that surface morphology plays a very crucial role. And then you find surprisingly they can be related to this fractal structure. This is what many people, including Professor Pandey and his group, particularly for strontium nitroxide, strontium oxide materials, they have shown. So towards the end of the third part of my lecture, I will try to bring out this connection with supercapacitor surface morphology with fractals. So that's the idea of my lecture today. So let me start with nonlinear dynamical system. So first we have to understand what is nonlinearity and what is a dynamical system. Why this nonlinear dynamical system is of interest compared to linear dynamical systems. I think most of the participants are physicists or engineers who have sufficient introduction or motivation towards physics problems. So I'm sure they're all quite familiar with some of these basic concepts. But I will try to introduce what is this nonlinear dynamical system in the simplest terminology, with simple examples. To understand physical systems, if you look at things around us, in this world, in this universe, one feature we can always realize: nature, nothing is permanent. Things change. Everything changes. Changes as a function of time. From the time of Big Bang, this universe has started expanding, and it's expanding all the time. It's 13.8 billion years. All through this time, the universe has been changing its state. Even today, tomorrow, animals are born, they grow and die. So do plants. Planets move around, chemicals change, crystals interact, clouds change their forms, and so on and so forth. Everything changes. So as Lord Krishna tells in Gita to Arjuna, change alone is unchanging. And Newton's laws represent such changes. Yes, all of us know, as students of physics. And Newton, in particular, the second law, the rate of change of momentum is directly proportional to the force acting on the system. Momentum, the vector in the three-dimensional Euclidean space, if the observer sits at the origin, for example, and he makes an observation of a particular system, it could be a pendulum, or it could be a planet, or it could be a spinning top, or a fly, or an aeroplane, whatever it is. So you can assign a position vector r, and a velocity vector, the rate of change of position. And so a momentum, vector p equal to mass into velocity. So the rate of change of momentum, we all consider Isaac Newton is perhaps the greatest intellect ever to be born on this earth, because standing on the shoulders of the giants of the past, he not only enunciated the laws of motion. Motion means everything moves, everything changes. So the laws of change. So he not only enunciated the three basic laws on which the whole edifice of science stands, he also identified an appropriate logical language, namely calculus, the art of calculating changes. So he said the rate of change of momentum, which you can put in this particular form, dp by dt, is directly proportional to the forces acting on the system, internal and external forces. So taking the proportionality constant without loss of generality to be 1, you can write the statement of Newtonian second law, dp by dt equal to force acting on the system. No force acts, no change. That's the first law. Every particle continues in a state of rest or of uniform motion unless acted upon by the force. But if the force acts, the state of the system will change. How it will change? The rate of change of momentum is equal to the force acting on the system, which is substituting P equal to mv, and V is nothing but dr by dt. And if you consider those cases where mass is constant, doesn't change, but there are important examples where mass also changes, like the firing of a rocket and so on. But for the time being, I will assume that mass remains constant as a function of time. So you have the equation of motion for representing these changes, a second order vector differential equation. Given the force will be a function of position and velocity. And in general, it could also change as a function of It could be also dependent as a function of time explicitly. So you have a second order vector differential equation in which you have a dependent variable, namely the state vector, the position vector R, which depends on the independent variable, namely time. Time is independent of our existence. Time flows all the time, whether we exist or not, in the forward direction. So time is independent variable, and the position, and so the velocity, they are all dependent on this independent variable. So you have a second order differential equation describing the behavior of the particular system like pendulum or a Kepler particle or so on, provided you know the forces acting on the system. Now this kind of differential equation can describe any particular pendulum. In this world there could be thousands of such pendulums of mass m and so on. But to specify the particular pendulum, particular particle we have in mind, you can represent physical system you want to understand as a point particle. I think somebody has to. Hello?
Yes, sir. Please continue, sir. Aishwarya, that he has done.
Yeah.
Aishwarya, you should mute your mic. Yeah.
Mute
sir,
the mic.
Yeah.
Yeah. So, any physical system under appropriate circumstances can be represented as a particle. Particle is a very beautiful concept which is as zero dimension but endowed with all other physical characteristics like mass, like angular momentum and so on. So you represent a particle by this position vector and you have this mathematical equation to represent its change. But it becomes the specific system you have in mind, you specify the initial conditions. Initial condition corresponds to initial position vector and initial velocity vector. Dot means dr by dt at time t equal to 0, reference time. So if you specify this initial condition, which is obtained by making observations, which means you are making connection with the physical system you have in mind, then the system evolves according to this mathematical equation, second order vector differential equation. Solving at all future time, you can find the position of this particle at all t greater than 0, and from which you can find r dot. So the state variables can be found uniquely in general. For a single particle system, you can generalize this idea for an n particle system and could be as large as 10 power 23 Avogadro number. You have 10 power 23 particles or 9 particles in the solar 8 particles in the solar system and the sun, the 9 particles. So by position vectors R1, R2, Rn. So you have for this collective n particle system a system of coupled n coupled second order vector differential equation. Okay. Like the particles in this room, 10 power 23 particles. These particles move, collide, and give and take away energy and so on and so forth, and equilibrium may result in. So you have a large collection of coupled differential equations. Knowing the forces acting on each of these particles, then Newton's laws, Newton's equation of motion tells that given the initial state of all these particles, subject to these particles evolving according to these coupled nonlinear differential equations, you can find the position vectors of all the particles by solving this mathematical equation, and so the velocities of all these particles, and so the state of the future particle, the future evolution of such a dynamical system. And this was what scientists, physicists have been doing during the 16th, 17th, 18th century and so on. And the great mathematical physicist Simon de Laplace once boasted that for a super intelligent, the future is as clear as the past. That means, give me all the initial states of all the particles in the universe, then I can predict the future as much accuracy as possible. So for a super intelligence, the future is as clear as the past. That's what Laplace claimed, Laplace dictum. But of course, all of us know this Newtonian description has several limitations. I said n particles. N could be very large, like 10 power 23 or more, the number of particles in the universe, and could approach infinity. But then if you have such large number of particles, very often you are not interested in the individual dynamics of each of these particles, but rather the collective dynamics, average dynamics, average mechanics, namely statistical mechanics. So in such a case, you can develop an average mechanics, namely statistical mechanics, that should be adequate to deal with that kind of system. That is the development of statistical mechanics. But then I said, given the initial condition, namely the position and velocity of each of these particles at a given reference time, t equal to 0, which means I assume that I can prescribe these initial conditions as accurately as possible, as I want. But of course, you know that this position and velocity, position and momentum, they are canonically conjugate variables. You know, from at or when you approach atomic or subatomic levels, microscopic levels, prescription of one of the state variables disturbs the other conjugate variable. The uncertainty, Heisenberg's uncertainty principle comes into picture. So you have to incorporate Heisenberg uncertainty relation into the Newtonian description, and you require quantum mechanics at microscopic level. It's not that Newtonian mechanics is wrong, but it is inadequate at that level. So you have to appropriately modify it. So also, you have not discussed about any constraint on these dynamical variables, the position and velocity. Of course, the position, if you consider the three-dimensional Euclidean space, the particles can live anywhere in this universe. What about velocity? You know, Albert Einstein in the early 1900s came and said that no, not all material particles can have any kind of velocity, any value of velocity. They are all restricted by the velocity of light. Only light can travel with velocity of light, namely c, 3 into 10 power 8 meters per second. All other material particles can only approach the velocity of light, never reach the velocity of light. So there is a restriction on there is an upper bound on the velocity the particles can reach. So you have to incorporate that, you have to specify in terms of special theory of relativity, which for massive particles have to modify in terms of general theory of relativity and so on. But in recent time, during the past 4 or 5 decades, we have also realized the form of the forces can also restrict or limit the kind of information that you can extract by studying this Newtonian equation of motion, leave alone the quantum mechanical principles or relativistic mechanical principles. Even under ordinary macroscopic dynamics, there could be limitations on the knowledge or information that you can extract. And that is defined by the nature of the force, whether this force is linear or not linear, non-linear, as a function of the dependent variables, state variables, namely the position vectors R1, R2, Rn, and velocity vectors. Time is an independent variable. So that doesn't define linearity or non-linearity. That's immaterial. It gives rise to only inhomogeneous equations. But the most important thing is whether the force is directly proportional to the state variables or not. That can have dramatic consequences on what you can extract from these equations of motion. And that is what led to our understanding of noble features when you consider nonlinear forces. So let me explain in terms of some simple examples. So let me take the simplest of the example, namely a linear harmonic oscillator, which each one of us are quite familiar. So the force, I'm just taking one-dimensional oscillator. The position vector R has three components, X, Y, Z, which are all functions of time. But I will assume that this oscillator vector R has component only along the X direction. So oscillator moving along the X direction only. The force, restoring force, is directly proportional to the displacement X. F equal to minus Kx. K is the force constant. Okay? Minus direction because minus sign because of restoring nature. So m d square x by dt square equal to minus kx, which I can rewrite as d square x by dt square plus omega naught square x equal to 0, where omega naught square is nothing but k by m. Here in this equation, I have used the shorthand notation dot. A single dot means d by dt. So double dot means d square by dt square, just a shorthand notation. So x double dot plus omega naught square x equal to 0. Subject to, so this is a differential equation. You have to specify the initial condition. So you pull the pendulum apart and allow it to oscillate. So the maximum amplitude is capital A, and at the point of release, the velocity is 0. So you give those initial conditions. So subject to those initial conditions, you can obtain the general solution as x equal to a cos omega naught t. You also find an interesting property, the frequency. So there is an amplitude, initial amplitude, and an angular velocity, omega naught. But omega naught is square root of k by m. It's independent of the initial condition A. Initial displacement, it is independent of the initial displacement. It depends only on the system dynamics, namely the force constant and the mass. So whatever be the initial state, this is not going to change. So the frequency, the angular frequency is independent of the initial condition. So x equal to a cos omega naught t. So that tells you how the system evolves, how the dynamics of the system. So dynamics essentially means how the system evolves as a function of time. Evolution of the physical system in time. So this simple harmonic oscillator evolves by the rule x of t equal to a, some constant, to cos omega naught t, which you can draw pictorially a time series picture. X of t versus t. because A is a constant. At t equal to 0, we fix the initial value, which I call as 1, for example. Then cos omega naught t tells you how it changes as a function of time. It oscillates periodically. The variation, the evolution is a periodic change. The amplitude changes periodically. Or the displacement changes periodically with period 2 pi by omega naught. T, capital T equal to 2 pi by omega naught. You can represent the dynamics equivalently in the phase space, namely x dx by dt or xp, whatever it is. You'll find it's a closed curve, okay, because of this periodic nature. So for an initial amplitude A, so this is the center, origin, and with initial amplitude A. If you change A, you will have another concentric closed curve, another concentric circle. Change A further, you will have another concentric curve. So that is the nature of the dynamics in the phase plane, phase space, what we call it. Okay. The phase variables are the position vector and the velocity vector, or the momentum variable, or the velocity position variable, and so on. Now, to this linear harmonic oscillator, you add a force, for example, it's a typical example, a force of the form x, which is proportional to x cube. Still restoring force, but now it's not only proportional to x, but it is also proportional to x cube. The corresponding coefficient I call as lambda or beta or whatever it is. Strength lambda. Now consider this force. Again, the rate of change of momentum md square x by dt square equal to f. Divide m throughout. Then you have x double dot d square x by dt square plus omega naught square x. Omega naught square is k by m. Lambda by m, which I had rewritten as lambda, into x cube equal to 0. So this I will call is not a harmonic oscillator, an unharmonic oscillator. For the reasons I will point out shortly. This equation, fortunately, can also be solved, but not in terms of elementary function, but you require a new higher order function. Some of you may be familiar, but all of you may not be familiar, but I just indicate what this function is. X of t equal to a cn omega t. It's an elliptic function, Jacobian elliptic function. There are 3 types of Jacobian elliptic functions, Cn, Sn, Dn, etc. Well, let's not go into the details of that. But a Cn omega t, capital omega t. And you can check that this is indeed true. And this capital omega, the new frequency is square root of omega naught square plus lambda a square. Observe, this is very important. The physical characteristics, which is the frequency, this Cn is also a periodic function, but of more complicated nature compared to the cos function. But observe that now the frequency, if there is no unharmonic force, lambda is 0, capital omega is just omega naught, as in the case of linear harmonic oscillator, because lambda equals 0, just harmonic oscillator. But if lambda non-zero, you find the frequency now depends on the amplitude, the initial value, initial displacement. The system kind of remembers its past. And that is the origin of all this novelty. So Frequency now is amplitude dependent, and in some cases it can become highly sensitively dependent on this amplitude, the initial state. The Cn function is characterized by a modulus and so on. You can check that this is of this form. I'm not going into the details. And you observe that when lambda is 0, no, this anharmonic force, k square is 0. In that case, Cn function becomes cos, the previous periodic function. But now it is a more complicated function. So this you call as an anharmonic oscillator because it's not a harmonic function cos or sine, but it's a more complicated function. And so you call this an anharmonic oscillator. And these kind of forces you call as nonlinear force because it depends, the force depends, is not directly proportional to the displacement, but it is proportional to the cubic power, x cube. Why should it matter? For the linear harmonic oscillator, if you go back to that equation, x double dot plus omega naught square x equal to 0, I said the solution of the initial value problem is a cos omega naught t. But as far as the second order differential equation is concerned, there are two possible solutions, x equal to cos omega naught t and x equal to sine omega naught t. You just substitute. You will check both cos omega naught t solves this equation, sine omega naught t solves this equation. Not only that, you can make linear combination of these two functions. You call x1 as cos omega naught t, the first solution, x2 sine omega naught t, another solution. You make a linear superposition, linear combination where a and b are arbitrary constants, arbitrary scalar constants. So a cos omega naught t plus b sine omega naught t is also a solution. You can combine them by using the standard trigonometric function. You can rewrite this as capital A cos omega naught t plus delta. I leave it as a simple exercise for you to find what is how capital A and delta are related to small a and small b. So this is a more general solution. In fact, this is the most general solution of that differential equation, x double dot plus omega naught square x equal to 0. So you see that you can express the general solution as a linear combination of two independent solutions, and they are two linearly independent solutions. You cannot express sine omega naught t as just some constant, proportionality constant into cos omega naught t. They are related by a nonlinear relation. Sine omega naught t equal to square root of 1 minus cos square omega naught t. So cos omega naught t or sine omega naught t are linearly independent solutions. There are other definitions for linear independence. If you want, this is sufficient. So linear harmonic oscillator not only has two independent solutions, their linear superpositions or linear combinations are also gives a general solution. This linear superposition principle forms the basis of all our mathematical techniques which we study in our mathematical physics courses. The Fourier series, the Fourier transform, the Laplace transform, the Green's function techniques, and all those techniques are based on the linear superposition principle. Using those linear superposition principles, you can solve any linear dynamical system, with linear force, even with time-dependent forces, you can solve them. You can write the general solutions, and you don't see any surprise. They will have some frequency, etc., which you can find in general. But if you consider this equation, x double dot plus omega naught square x plus lambda x cube equal to 0, then you find let x1 be a solution, x2 be a solution satisfying that cubic equation. I ask the question, can you have a solution which is a linear combination of x1 and x2, just like the harmonic oscillator. So x1 satisfies the cubic equation, x2 satisfies the cubic equation. Can one have a general solution which is a linear combination of these two? And you find it can never be a solution except for the special case both a equal to 0, b equal to 0, which is a trivial solution. So these kind of equations fail the linear superposition principle. And I said that linear superposition principle forms the basis of all our knowledge about solving differential equations, dynamical systems. Almost all our dynamical systems are represented by differential equations. And as long as they satisfy linear superposition principle, all the mathematical techniques that are available can be utilized. But if you have this kind of equation, even in the simplest modifications, lambda x cube is an example. You can have lambda x square, lambda x power 5, and so on and so forth. Okay. So for nonlinear systems, linear superposition principle fails from a mathematical point of view. Since dynamical systems, when you have nonlinear codes, are represented by nonlinear differential equations like this differential equations. These equations also in general cannot be solved by the methods that one is familiar with. Consequently, each nonlinear differential equations representing a dynamical system is in general a class by itself. So they can lead to a lot of novel consequences. And that's what I will briefly discuss today. Okay. So I will very quickly try to move forward. So for example, just to put these linear dynamical systems in a little more perspective. For example, you can consider the most general linear differential equation with constant coefficients. Dynamical equation for a forced LCR circuit, which all of us are familiar with appropriate variables, so current or voltage, and M, alpha, omega naught, they're all related to LCR variables. So you have a differential equation like md square x by dt square plus alpha dx by dt plus omega naught square x equal to f sine omega t. We can redefine and you can simply write the dynamical equation as d square x by dt square plus alpha dx by dt plus omega naught square x equal to f sine omega t. So you can analyze these equations and you will find it consists of two parts. I mean, there are underdamped, overdamped, the critically damped cases and all. So let me consider the simplest one, the underdamped case. In that case, you will have when you drop this external forcing f sin omega t, that is equal to 0. You have the damping alone present. The damping is proportional to the velocity term, alpha dx by dt. So you have the original periodic motion slightly modified, and then it's exponentially falling off part, damping part. But if you include the forced part also, f sin omega t, external force, then you find the solution consists of two parts, namely the auxiliary part, the complementary function. So this first part corresponds to damping, so without the external forcing, and then there is a resonant periodic oscillation. So you observe that there is a natural frequency omega naught, but there is a new frequency omega, which is the frequency of the external forcing. So this part, if you wait for sufficiently long time, because of the presence of e power exponential minus alpha t, it falls off exponentially, and what remains is just the periodic oscillation AP, a fixed frequency, a fixed amplitude, cos omega t. Omega is the frequency of the external periodic oscillation. So this is the resonant periodic oscillation. It's called a limit cycle, limiting periodic motion. System starts resonating with the external forcing, resonant periodic forcing. That is what damped force oscillation. This is what the most general linear systems. You can also, through example, I can demonstrate this. In the x dot plane. First, for the damped harmonic oscillator without external forcing, so with just the damping term with the damping parameter alpha. So this is the phase plane, x dot plane. I have given the exact solution, but you can schematically see how the dynamics behaves. So you start somewhere in the phase plane, the initial state, then you ask the question how this phase trajectory travels. You find it starts spiraling because of that exponential term, and then because of the cos terms, it periodically changes and ultimately it approaches the origin, the damping. That is one aspect. So this is for critical damping that I'm not going into. But in the picture C, what I'm showing is that you consider the dynamics corresponding to another initial condition. It could be even far away from that. Then you ask the question, what happens in second new initial condition? Again, it starts spiraling and it approaches ultimately the origin. So when you consider these two trajectories, you ultimately find they converge. The distance between them do not change dramatically. They are just finite values and ultimately it becomes zero. Similarly, when you apply external forcing, F sin omega t, you find for an arbitrary initial condition, you plot x versus t, for example. Initially, there is some variation. But then if you wait for sufficiently long time, the system starts resonating with the external periodic force omega, and you have a completely periodic motion, resonant periodic motion. Or in the phase space, you start somewhere in the phase space, and then you allow the system to evolve. So initially, you find that the amplitude keeps increasing. Ultimately, it ends up in a closed orbit, closing, limiting periodic trajectory, the limit cycle periodic motion. So it ultimately ends up in a limiting periodic motion. Similarly, if you start from outside the circle again, it will spiral and it will end up in this limiting periodic motion. That is the resonant periodic motion. Now my question is, what happens if I include nonlinear force? First, anharmonic oscillator I have already mentioned. It exhibits periodic motion, but not in terms of harmonic function, but more complicated elliptic function whose frequency depends on amplitude. Okay. So because of that, when you change the amplitude, then the wavelength will also change. In the case of free oscillator, you can consider damped oscillator also. There is also some changes, but more importantly, the most important oscillator is the damped forced anharmonic oscillator. Yeah. So this is the typical nonlinear dynamical system I would like to consider. It is one of the simplest nonlinear dynamical system we can think of, where you find, again, it's a Newton's equation of motion, the rate of change of momentum, mx d square x by dt square, equal to force acting on the system, so damping force, minus alpha x dot, then minus omega naught square x, plus lambda x cube or beta x cube. I change lambda to beta just for convenience. Okay. You can also have a double well potential, so I will take minus sign. which is actually I'm pointing out the double well, which is called the Duffing oscillator. The dynamics of a triode valve can be represented in terms of such. The current voltage characteristics can be represented by this kind of equation equal to F sin omega t. Now let me try to understand this dynamical system. If this beta is 0, just now I showed you can completely integrate. You can obtain resonant periodic solution analytically and you can represent them pictorially. But when you include this cubic nonlinearity also, then the entire mathematics completely breaks down. It will not help you to analyze the simple second order scalar differential equation, but non-linear. There is no way to solve this equation exactly analytically. You find many complexities arise when you want to solve this numerically. Of course, you can apply perturbation techniques, approximation techniques, etc. I'm talking about exact analytic solution. It's impossible to find, at least till now. But what you can do is you can numerically analyze. So this is what during the past 3-4 decades people have been trying to do. Say Runge-Kutta fourth order method. Now let me analyze this for minus sign. You can also do this for plus sign, but minus sign is somewhat interesting, more interesting. So I am doing that. With minus sign, you will find there are 3 equilibrium points. That is constant solutions. X double dot 0, X dot 0, and F. When F is 0, then you will find X equal to 0 is possible equilibrium point. X equal to 0 means X dot is also 0. And then you will also have omega naught square minus omega naught square plus beta x square is also equal to 0 is also possible, which gives you 2 roots. So one at the left side and another at the right side. So there are 3 equilibrium points on the x-axis. So the system will end up with one of these equilibrium points when you have just damping alone, when there is no forcing. So what I'm trying to do is numerically analyze the system for different values of external forcing strength. You can do any of the parameters. There are actually 5 parameters, but you can show that after scaling there are 3 independent arbitrary parameters. I fix 2 of these parameters and vary this F alone. When F equal to 0, it's purely damped oscillation. My initial condition is such that it approaches the left equilibrium point. Now, I give a non-zero external forcing, F non-zero, F equal to 0.1, 0.2, 0.3. Then I find the phase trajectory. I analyze this numerically and plot x dot in the x dot plane, the nature of the trajectory. After leaving the transients, you find a closed curve. A closed curve in the phase space means what? It's a periodic orbit, the periodic orbit with period equal to t, capital T equal to 2 pi by omega, because that is resonant periodic oscillation in the linear case. The same thing happens even when you include the nonlinear force for small values of beta and small external forcing strength. That's all fine. Through perturbation analysis, you can try to find an approximate form for this periodic motion. Next comes the most interesting thing. You keep increasing F. This external controlling parameter, because this parameter is in our control. So you vary this. We find that F equal to 0.35. There is a sudden, this particular motion, periodic motion, period T equal to capital T equal to 2 pi by omega naught, loses its stability, and in place of it, a new periodic oscillation, but which takes twice the earlier time period to come back to the original value. So a periodic oscillation, but with period 2t, the period is twice the period, the previous period. So 2t periodic oscillation comes up. So capital T, 1t periodic is 2 pi by omega naught. 2t means you multiply that by twice. So for f equal to a critical value, which I call as approximately 0.35, so at that the system bifurcates from one kind of qualitatively one kind of dynamical behavior to a new kind of dynamical behavior. Period T, from period T you get period 2t. You increase f even in smaller intervals. F equal to 0.351, 0.352, 356. Then finally at f equal to 0.357, you find this period 2t loses stability, and in place of it you get period 4, 2 power 2 periodic oscillation emerges. And this periodic oscillation lives for some more values of external forcing strength, and then it again bifurcates at some other critical value f equal to 0.3578 or something like that. Then you have 2 power 3 period 8 oscillation, then period 16, period 32, 2 power n, and ultimately at f equal to 0.365, 0.357 here, 0.365, not much variation, but within that you had several bifurcations. Each time the period doubles, period doubling bifurcation. Ultimately it ends up in a complex motion. It's called chaotic motion. Chaotic dynamical behavior, chaotic oscillation emerges. The left well, similarly, if you have started the different initial conditions, the right well, you may have a periodic chaotic oscillation like that. If you keep increasing f, newer and newer kinds of behavior may emerge. So all of them can be succinctly, briefly, clearly put down in a bifurcation diagram, where I have plotted the maximum value of this periodic orbit versus the strength of external forcing F. So for lower values of F, until F equal to 0.33 or 334 or something like that, you find there is only one periodic oscillation. It has one maximum value. So here I have one for every f value. You have one x value, the maximum x value. So period 1 orbit, that is period 1t. But then suddenly at a critical value f equal to 0.35 or something like that, instead of one
sir, may I ask?
Possible values. So that is period 2t. Then at another critical value you have period 4. And in smaller range you have period 8, 16 and so on. Then you have infinite number of possible solutions. And that's where you have this complex motion.
Here.
Yeah. Any questions? Anybody wants?
Sir, so the period you are talking about t, is it 2 pi by omega or 2 pi by omega naught?
The period t equal to 2 pi by omega, the external forcing period. Because here the system for small values resonates with the external forcing. Okay. It's not 2 pi by omega naught, but it's 2 pi by omega, the external forcing strength. And then that period doubles. Okay. Twice t, 4 times t, and so on. Is that okay? Somebody asked?
Yes, sir, I got it.
Yeah.
But sir, like if your f is small, although I understand since it is a first oscillator, eventually it will oscillate with 2 pi by omega. But are not we supposed to see effect of omega naught for some small values of f?
No, only when beta equal to 0, it for f equal to 0, beta equal to 0 only, you have 2 pi by omega naught. Okay, that is the natural frequency. But when you have external forcing, as I pointed out earlier, the solution will have two parts. One part exponentially falling off due to damping, and that will contain omega naught and all. That part will fall off and go to 0, but what remains will be the periodic term with periodic oscillation with external forcing.
Yes. Okay. I
And
got
that will continue even with when you include nonlinearity also for small values of f. So that is the resonant periodic oscillation, period T oscillation I am pointing out here, which then gets doubled every time as you increase f at critical values. And ultimately, you can get infinite possible values, and that corresponds to complex motion, chaotic motion. So this is one possible route by which the dynamical system becomes and takes complex motion, a single scalar second order differential equation, a dynamical system represented by a single scalar second order differential equation with a nonlinear forcing present and external forcing also present. It shows all this complex motion. And when you go beyond this period doubling, chaotic behavior, you can ask the question, how is it always chaotic? No. There could be very many kinds of further bifurcations, extremely sophisticated kinds of bifurcations. I'm not going into the details, but it's very fascinating. One can never claim that the study is complete because this is only numerical. Yes. Under certain interval change in F, you come across this bifurcation diagram. But if you go to even smaller, finer scale, some new features may arise. So in the absence of analytic solutions, numerical solutions can never be complete. And this is only for change in one parameter, F. What about change in beta? What about change in omega? So when you try to change many of these parameters, then the bifurcation diagram becomes extremely complicated in the 2-parameter phase diagram, 3-parameter phase diagram, and so on. The dynamics of this oscillator becomes extremely complex. Now, what happens in this chaotic regime? Why I call this chaos? So here I have plotted the dynamical variable x, the displacement, as a function of time for a choice of parameters for which you are in this region of the bifurcation diagram, like f equal to 0.36, something like that, where the system shows this kind of phase plane structure. At that value of f, you plot x for a certain initial condition as a function of time. So I plot this in terms of blue curve. There are two colors you can see. One is blue and one is orange. This blue curve, you find you start from certain initial value and the system dynamics following that dumping oscillator oscillates not periodically but aperiodically, but bounded, because this dynamical system is a physical system. The dynamical variable cannot grow to infinity. It is bounded between, say, minus plus 1.5 and minus 1.5. Within that bounded values, the system exhibits aperiodic, non-periodic motion. Okay? That's fine. If you proceed further, it will be like this. But next, what is important is, I'm integrating this, asking the question, suppose I start from an extremely nearby another initial condition compared to the previous one. And mark the points by this pink color. How does this new initial condition evolve for the same equation? Well, I integrate. Initially, I plot, and I do not see any difference. Both the colors follow each other. Color curves follow each other. But then at finite period, some t equal to 30 time units in normalized units, I find these two trajectories deviate. But then when I increase the time, again they rejoin. I wait for sufficiently long time, 40 or 45 or 50 time units, then you find that these two trajectories separate out. Separate out, and separation can sometimes becomes as large as the system size. But since I can have only bounded motion, this deviation then again becomes small, but then again they increase. Then if this proceeds like this, but the important point is an extremely small deviation, even in the order of third decimal, fourth decimal, fifth decimal variation, you find after finite time, they lead to a very large deviation, as large as the system size itself. As a consequence, prediction of the future behavior becomes extremely complicated and it's impossible. So this is what the more clear picture of the dynamical state, the bifurcation diagram, and corresponding representation in terms of Lyapunov exponent. I'm not going into the details, I'm running out of time. But this is what made Henry Poincare. He was not studying this Duffing oscillator, but he was studying the two-body problem. I mean, the sun and the solar system, the sun and the earth, for example, sun and a planet. That problem is completely solved. You have the Kepler's law, three Kepler's laws. Planets move around the sun in elliptic orbits and so on and so forth. But then he asked the question, suppose, of course, in the solar system, in addition to Earth, you have other 7 planets. You consider the motion of a third planet, a second planet, so that you have a 3-body problem instead of 2-body problem. So the sun, the Earth, and Venus, for example, or Mars, for example. So consider the effect of Mars also on the motion of the Earth. What happens? Again, you have inverse square force type law. So you can write down the equation of motion. You solve the equation of motion. After enormous amount of calculation and analysis, Henry Poincare, during the beginning of 1900, he came to the conclusion that problem, 3-body problem, cannot be solved exactly. Even today, this problem cannot be solved exactly. And he said, it may happen that small differences in the initial conditions produce very large ones, very great ones in the final phenomena. Just like this. Very small differences in the initial state leads to very large changes in the final phenomena. A small error in the former will produce an enormous error in the later. Prediction becomes impossible in such nonlinear problems under appropriate conditions. It's what in 1962, Edward Lorenz, an atmospheric physicist, who analyzed the weather dynamics, the underlying Navier-Stokes equation. He reduced the dynamics under appropriate assumptions to a bare minimum form of equations of motion in the form of a system of 3 coupled first order ordinary but non-linear differential equations. When he analyzed that in those days with the simple computer that were available, he again came across exactly the same phenomena, sensitive dependence on initial conditions. Small changes in the initial condition can lead to very large changes. So that he came to the notion of butterfly effect. As small a perturbation as a butterfly fluttering its wings somewhere in the Amazon in the South America forest, can in a few days' time grow into a tornado, cyclone-like situation in Texas, in the state of Texas in North America. Small change as a butterfly fluttering its wings in the forest of Amazon has led to a weather which is extremely complex. But the idea is that if that butterfly had not fluttered its wings, the weather would have grown in a few days' time into a normal way, into a smooth way. But just because of the small perturbation, the weather dynamics has changed so dramatically, the evolution becomes uncontrollable, unpredictable. What? Prediction becomes impossible. So, the simple example of Duffing oscillator dynamics under appropriate circumstances. Not everywhere. Here it's all regular motion. But the parameters, the control parameters, the dynamical parameters are suitably chosen, then the system can show extreme sensitivity to initial condition so that prediction becomes impossible. Small change can lead to very large change. It's what ultimately one ends up. It's not only that, in those cases where your system exhibits complexity, chaotic motion, you can also represent the dynamical state, which I called in terms of this complex behavior in the x dot plane. Okay, I just projected the dynamical state because it also depends on the external forcing T, projected in the x dot plane, and I got this picture. But I can also plot a three-dimensional picture that is x dot and time as third axis, and then cut off at every 2 pi by omega times, every capital T times. So the trajectory, you consider the trajectory in that plane, T equal to 2 pi by omega. So that's called a Poincare surface of section. In that surface of section, you consider x versus x dot for this Duffing oscillator. The trajectory looks like this. It doesn't fill the entire two-dimensional surface x dot, but it's a kind of curve. But whether it's a curve in the two-dimensional plane, it's just a single curve, or what kind of nature is it? You can also, if anybody is interested, you can also take a simple exercise. It's a map. There are two variables, x and y. And there is an independent variable I call n. N is an integer. N runs from 0, 1, 2, 3, etc. infinity. So, at n plus 1th instant, the variables x and y are given by the values of the variables at the previous instant, xn and yn, in this way. So with a simple calculator or a computer, you can work out how this dynamics behaves. It's called Heinan's map. Okay. Then if you plot x versus y, it will have this complicated structure. But what is interesting in this, one thing I pointed out was sensitive dependence on initial condition. Extreme sensitivity to initial conditions. Another thing is self-similarity. Okay. So you consider this attractor, because this is a chaotic attractor, because the dynamics, wherever you start with, ultimately the system, the dynamics ends up in this curves. You take a small region somewhere here, okay, magnify that. So this appears as if as a continuous curve. Actually, it's not. So you magnify this. If you magnify this, you'll find there are 3 such curves. And you take a small portion, you magnify this. Again, you have a similar structure. And you take a small portion, you magnify this. Again, you have a similar structure. So structure within structure, self-similar structure. Similarly here, you take a small area here, magnify, and then you have this picture. You magnify again these 3 curves, magnify again these 3 curves, and it goes ad infinitum. So structure within the structure. So they are not 2-dimensional curves, they are not 1-dimensional curve 1, but it's somewhere in between. In fact, there are methods to find the dimension of such figures. You find they are fractional dimensional objects, entities. The dimension for this Duffing oscillator, this particular value of parameters can be calculated as 1.38 or something like that. But this Hanna-Natt factor is 1.26, so-called box counting method and so on. So self-similarity. So that is what these chaotic attractors exhibit. Sensitive dependence on initial condition, self-similarity, and many other features. Okay. Then you can ascribe many other associated properties with these chaotic attractors, but this property, self-similarity, which is of interest to me in the present lecture. Okay, so I think I have already spoken for almost 1.5 hours. Only now I have come to somewhat 1/3 of my talk, but I will try to rush through the remaining part. Okay. Well, there are many, in recent times, many examples in the nanophysics, nanomechanical resonators, NEMS, nano electromechanical resonators. So, Anand Venkatesh, a young faculty member from Isar Mahali and his group, have recently identified nonlinear damping in palladium nanomechanical resonators, and they have shown from their experiments, they have related this to some of the properties of Duffing oscillator, Duffing-like damping I have mentioned. But anybody interested, you can look into these articles. Well, there are other simple examples, but I will not go into the details. Showing sensitive dependence on initial conditions, chaotic attractor, self-similarity, this logistic map. The simple map is not a differential equation, but it's a simple map. For example, the population of species. You know the population at the present instance, then the population in the next instance is given by this equation. AXN into 1 minus xn. So the last term is absent, it is just directly proportional. It's a linear map. Now, because of this A minus AXN square, it's a non-linear map. You study these properties, you can find even some exact solutions. Unfortunately, I cannot go into the details, but all this sensitive dependence, period doubling, etc., and how this critical values bifurcation occurs, and it goes as a universal, it leads to a universal number called Feigenbaum's universal number and so on. You can find, I think I leave it as an exercise to you. So I come to the next part of my talk. I promised to talk about fractal objects. We already came across a fractal entity, namely the chaotic attractors. Okay. They show structure within structure which is similar to the previous one. Something like cauliflower. So you have a big flower, you peel off one part, then you find you have similar structure than like the original one. And you remove, again, consider a small part, again you have almost similar structure. So on at least 4 times you can see such structures. self-similar structures. So fractal is an object or a mathematical set with self-similar pattern, a terminology coined by P.B. Mandelbrot. Fractal because you can associate a dimension which is a fractional value. In the sense, this object, this entity, is a sprawling and tenuous pattern which, when magnified, reveals the repetitive levels of detail so that self-similar structure exists at all levels. So that is the definition of fractals. So you see, as I have shown in the chaotic attractive Duffing oscillator, general characteristics of fractals are fine structure, self-similar patterns, and this notion of non-integer dimensions, about which I will come quickly. So mathematically, such structures have been identified for the past 2 centuries and so on, starting from perhaps Cantor, Koch, Helge von Koch, Václav Sierpinski, Gustav Julia, Felix Hausdorff, mathematicians, geometers at different points of time. Until recent times, after chaos, etc., came, Mandelbrot from France, I think, for example, defining the dimension of the coastal line of British Islands, and so on and so forth. So, okay, he came to the conclusion that there exist in nature many entities which have such structure within structure. As I said, cauliflower or ferns, black spleen fern, sponge, growth pattern of some crystals, branching of certain blood vessels, clouds and coastlines sometimes. Then mathematical sets, Cantor set, Koch curve, Julia set, Mandelbrot set, etc. They show the self-similar pattern. I will explain. So some of you may have seen these nice entities earlier, but for others, you may not have noted these properties. So let me consider an infinite set of points on the unit interval, not integral, sorry, interval 0 to 1. So let me consider a line of length 1 unit. So to start with, I call as S0, the set S0. Just this full line. Okay. So I have 1 unit epsilon, and the number of entities is 1. So M is 1. Now I mark this unit line after each 1/3 units. At 1/3 length, I mark a point. Then 2/3, I have another point. Then remove the middle part. Delete the middle part. So this is the figure I get. Okay. The middle part has been deleted. So I have 1/3 length 1 unit, and 2/3 to 1, that is again of length 1/3, another unit. So I have 2 units, each of length 1/3 in the set S1. The set S1, I have 2 units and each of length 1/3. Next, I do the process again. So take each of these units, divide into 3 equal units. So mark that point, then drop the middle one. So I have a 1 unit from 0 to 1/9, 2/9 to 1/3. The middle unit has been dropped. This is already dropped. And here again, I drop the middle unit. So how many non-zero units I have? This is 1, this is 1, this is 1, this is 1, this is 4 units. M, the number 4. And what is the size of each unit? Length of each unit is 1/9. I do this process again. Take this unit, divide into 3 parts, and drop the middle parts. So how many parts here? I have 8 units, and each one of size 1/27. So I proceed this ad infinitum. As n tending to infinity, what is the structure? and that is what Cantor set corresponds to. Okay. So sequence of deletion operation. To start with, S0 is 0, 1, the entire entire unit interval. But here I have the middle part dropped, here 3 parts dropped, and so on, repeat k times. So at the kth level, obtained by deleting the middle of each of the intervals in the set Sk. So if I proceed with this set, the set has a self-similar property. So if you take each of this unit, expand, and then you have the same, this unit, ultimately. So original structure is maintained in each of these units. The part 0, 1 over 3, 2 over 3 to 1 in S1 are geometrically similar to S0. S0 is just full unit length, except that they are scaled by a factor 1/3 because their total length is 1 over 3. Again, the parts of S2 in each of the 4 intervals are scaled by a factor 1 over 3 square because each unit is of size 1 over 9 of the original unit. That means they are scaled by a factor 1 over 3 square. So this proceeds ad infinitum at the kth level, so that individual unit are scaled by 1 over 3 power k. As a consequence, you can define the fractal dimension as df, as df equal limit epsilon going to 0 minus log of m epsilon by log of epsilon. Actually, the minus sign comes because you can write this as log of 1 over epsilon. Okay. Because if the original unit is 1, then the next is 1 over epsilon square, 1 over epsilon. That's what you have, log of 1 over epsilon. Okay. So as a consequence here, in this particular case, you have at the kth level, you have 2 power k units, and each one has a size 1 over 3 power minus k. And so log of k is k, log of 2 power k is k log 2, and log of 3 power minus k is minus k log of 3. So minus goes off. You have log 2 by log 3, which is 0.631. So in the ultimate state, after ad infinitum, this set S infinity takes a dimension. It's not 0 dimension, it's not 1, but it's a dimension 0.631, the Koch curve. So calculate the total length of the Cantor set. At step 0, its length 1. Its length is 1. At step 1, its length is 2 by 3 because middle part is dropped. 2 by 3 is around 0.666. The next step it is 0.44, and third step it is 0.296, etc., etc. So as n tends to infinity, total length decreases and approaches 0, as well as the length of individual segments also approaches 0 in a faster way. So dimension of the set simply gives the relation between the number of segments m and the length epsilon of each segment. And for Cantor set, the fractal, the non-integer dimension df is 0.631. Similarly, I will show another example, simple example. Consider, take an equilateral triangle. Divide each side by 2. Okay, like this. Mark the center of this side and center of this side and center of this side. So connect these points, 3 points. So how many triangles you get? 1, 2, 3, 4. Drop the middle part. So that is the white part. So that is the stage 1, set 1. Then do the same thing for the next stage. Take this, take each of this triangle, divide, mark the middle part, points here, here, drop the middle, and then you have 4 triangles, drop the middle one. Similarly for this triangle. Similarly for this triangle. So you have this figure. So you keep on doing this. And what you ultimately get is the Sierpinski triangle. So start with an equilateral triangle, connect the midpoint of the sides with line segments, remove the middle triangle of the 4 triangles formed. Continue the iterations. So what the end result? What is the end result? It leads to a very porous open figure like a triangular filter. The completed Sierpinski triangle naturally decomposes into 3 triangular parts, an upper portion and 2 lower portions. Okay. An upper portion and 2 lower portions, each of these things. Sorry. Each of these parts are exactly replica of the whole original figure. Likewise, each of these parts itself can be decomposed into 3 similar ones again, etc., etc. That's repeated. Okay, so these are the first few successive steps of constructing Sierpinski triangle. And what is the dimension then, following the earlier definition? So the number of units at the kth interval 3 power k, and the corresponding the interval 1 over 2 power k, and so it is 1.585. So non-integer fractal dimension. Though there are many other things. You take an equilateral triangle, 3 triangles divide, and at the middle part into 3 parts each side, and then add another triangle for each of the sides. Then you continue. You get a snowflake like 3 congruent parts and so on. So that's another self-similar structure. Julia set for a complex number. For example, z of n plus 1 equals zn square plus c. C a complex number, zn also complex number, xn and plus yn. So in the complex plane, xy plane, if you plot these figures for appropriate values of c, it takes such a complex structure, but self-similar structure. Similarly, the Mandelbrot set, when written in terms of real, Julia set written in terms of real variables. So that shows this kind of structure, etc. And you can also have multi-fractals with not only one fractional dimension, but you can have a spectrum of fractal dimensions. You can read to multi-fractal objects and so on. So there are different ways of finding the dimension of this fractal objects, the so-called box counting, Higuchi algorithm. Many algorithms are available. So I'm just concentrating on these 2 parts. Box counting. So what is it? It's defined in terms of the number of boxes, the n epsilon of linear size epsilon, required to cover the set. So it's exactly what I have done here. Yeah. So the number of linear boxes, m boxes, each one of size 1 over epsilon. So defined in terms of number of boxes, n epsilon of linear size epsilon required to cover the set. So for smooth integer dimensions, n epsilon is epsilon power minus db. You generalize this to this fractional cases, self-similar cases. Then you have db in the limit epsilon tending to 0 minus log. From this, taking log on both sides, you get log epsilon going to 0 log n epsilon by epsilon. So this is what the dimension I have used. Yeah. So now I come to the final part. So how about time? So I think I can manage. So any questions on these fractals? Anybody has? I don't know how far I have taken the audience with me, but I think these are simple concepts I have tried to point out. Any questions, any points anybody has raised? Pandey?
Probably that at the
Okay,
end of the lecture that maybe.
Okay,
Yeah.
I will proceed then.
Yeah.
So now I come to the last part of my talk. As I pointed out in the beginning, for this workshop on energy storage materials. So as you have been hearing many lectures during the past 4 days, including today, so many talks on energy storage materials, but particularly supercapacitors. So what role these fractals, the notion I have introduced, nonlinear dynamics, and then chaotic, particularly chaotic dynamics, the self-similar structured attractors, in particular having fractal dimension. Does it have any connection with supercapacitors? As you might have already familiar, that the properties of the supercapacitors and supercapacitors, as we have been repeatedly told, they are very important for energy storage and for future applications in many areas. So these supercapacitors, they have a surface that they are formed on I mean, they have two-dimensional surface, thin films, and these have surface morphology, particular surface morphology, and this surface morphology plays a very important role in the performance of the supercapacitors, as I think you will all agree. And in particular, certain oxides and metal ions doped play a very crucial role. And this is what Professor S.N. Pandey and his group, for example, a student Kavyashri, recently she got a PhD, and many of his group people. I mean, many people have analyzed the surface morphology from fractal point of view. In particular, Professor Pandey and his group have studied, I think, many oxide films, in particular, undoped, copper-doped, iron-doped, and yttrium-doped strontium hydroxide. Thin films. These are thin films, not these films. Sorry, these thin films by Professor S.N. Pandey and his group. I will give a specific reference towards the end. So they have prepared the samples by successive ion layer adsorption reaction, which I'm sure you all heard about, CLR technique, and field emission scanning electron microscope techniques using this FESM technique. Morphological studies have been carried out. So essentially, you study the height of, you divide the two-dimensional surface into n square number of pixels, and then you measure the height of these individual pixels one by one, and then you apply the different techniques I mentioned for finding the fractal dimension, like box counting, Higuchi algorithm. I mean, there is a new algorithm called Higuchi algorithm, or any other algorithm. Many algorithms are there, and the Higuchi algorithm can be useful. Is quite useful to study fractal characterization of SEM micrographs of prepared samples. And when you analyze this, then you find that all these thin films, whether undoped or doped with these metal ions, show distinct fractal characters. These fractal characters, fractal dimension, etc., they are directly proportional to what you observe in electrochemical characterization. And that confirms that study of fractal analysis, the roughness nature of these films is characterized by the fractal dimension. which is also characterized by the several electrochemical characterization properties. And consequently, you can be confident that deposition of thin films show nonlinear behavior, as I have pointed out in the case of Duffing oscillator or Hennen system and so on. So, to analyze the complexity or irregularity of surface, one can use fractal analysis in a purposeful way, which will provide deeper insight into the surface morphology. So, this is the idea that I would like to very briefly point out. So, the standard techniques I will to study the properties of these thin films is during the. So, what do? You deposit these materials. The particles. So, what happens? The particles are randomly deposited on the substrate. Okay, you choose an appropriate substrate. So the way in which these films are deposited can change from material substrate to substrate. So depending on the nature of the substrate, you can have different kinds of thin films formed. So this randomness causes roughness on the film. And roughness is quite essential parameter for characterizing the morphology of films. So how do you characterize the roughness? So you take the two-dimensional surface, you identify n by n pixels, so n square pixels. So and denote each of these pixels through these two indices ij. And the films are deposited on the substrate. So you can find at each of the pixel the height of deposition, the surface height of the thin film. So I call that as Yij at the pixel ij. Then you can take the average value of these heights over these pixels. So expectation or average of Yij, the mean value of Yij, the heights over a surface of side L. So which is nothing but sum over j equal to 1 to L along the horizontal axis, along the vertical axis in the two-dimensional plane. And then divide by the total length 1 over L. Or is it 1 over L or L square? I think. Pandeji, is it 1 over L or L square?
It should be there, sir. Sir really pointed out that 1 over L square because two-dimensional view in there. Yeah. Yeah,
it should be 1 over L square. Yeah. So Y average of mean value should be 1 over L square of this. So knowing this mean value, then you can associate several vertical properties of the surface. Vertical properties of the surface. So you have the mean, deviation from the mean, okay, at each point. How much at each pixel there is deviation and its magnitude. Average interface roughness, RA. So that is nothing but the expectation of this quantity, the average of this quantity, average interface roughness. So that's a measure of interface roughness. And then root mean deviation. So again, the mod square root of this root mean deviation. So you can define. So that is for vertical. You can also consider lateral correlation, lateral surface correlation, which is also an important characteristic of surface. So all these things can be analyzed using the following measures. So autocorrelation function, like h of x of, or you consider the fluctuation in height, and then you take the average of that. So the correlation between sides x plus r and x. And this autocorrelation drops off and it becomes minimal if this R is much greater than the correlation length psi. So that's a standard property. Then you can also talk about height correlations, that is hx plus r, hx square, and then its average. If r is much larger than psi, then it's 2 omega square. Omega is the root mean square deviation, which I pointed out. and R is much less than this. This is R power 2 alpha, where alpha is called the roughness coefficient. Okay. So for smooth surface, the difference in surface heights at 2 points proportional to the distance. So that you can define. And for lateral distance, for many rough surfaces, one can show the at the height at x plus r minus x. The mean, if you take that, it goes like r power mod r power alpha. And this exponent alpha is the roughness exponent. And the lateral distance is scaled by a factor epsilon, that is x plus epsilon r. You consider the distance by an epsilon. H of x plus epsilon r minus h of x, average over x. That is nothing but epsilon x plus epsilon r, because by definition you can call as h of x plus r minus h of x, or h of epsilon x minus h plus r minus h of x. So I've written h of x, epsilon x plus epsilon r minus h of x. So that goes as epsilon mod epsilon r power alpha, which is epsilon power alpha f of r. Showing that average height separation will scale by a factor epsilon power alpha. So the exponent alpha is the roughness coefficient. When alpha is 1 means the surface is smooth. As the value of alpha decreases, surface becomes more and more rougher. So for large scales, not scalar, for large scales, the fluctuation, saturation, and roughness has been obtained. What is it? I think something is missing. Okay. So let me go to. So one can also obtain a relation between roughness exponents and the box counting dimension. As I think you can go through the steps. It can be obtained as dB equal to d, the dimension plus 1 minus alpha, the roughness exponent. So if d is the dimension of the substrate, then the box counting dimension dB is related to the roughness through this particular relation. So you can use this relation suitably once you have the box counting dimension, or you can find the fractal dimension using the Higuchi algorithm. So what this algorithm tells about? As we have already seen, thin film surfaces generally show fractal structure, which is a self-affine structure. Higuchi algorithm is originally deduced for time series analysis, like in the case of a Duffing oscillator or in geophysical context. But this, in recent times, is also being used for surface technology. So what do you find this from here? So I said you have n by n pixels, so totally n square pixels you can consider on the surface, the thin film surface. So, and these pixels you record by same image, you take the same images and calculate the heights of each pixel. Divide this n by n plane into horizontal sections or vertical sections, whatever is convenient. So for example, a horizontal section. Okay. Then each pixel, each pixel of a horizontal section, take a particular horizontal section, then you have n pixels. So you measure the heights as z of 0, z of capital Z of 0, capital Z of 1, capital Z of n. Now, from out of these n measures, which you obtain experimentally, you can develop k subsequences. So, for example, horizontal m equal to 1, 2, 3 k up to k, and for example, vertically, you can go up to K, some K maximum. So by taking points like z of m plus K, so each of these values are given here. Z of m plus 2K and Z of m plus Pk, where P is such that n minus m by K, so that is the integer. If n is 100, then 100 minus, you take m and K, so that you approach n, the maximum value of n, and the corresponding integer value you take. So that is what P means. So once you have this subseries, then you can define for each of this segment ZMK by taking deviations between appropriate neighbors in this particular fashion, a length with some appropriate normalization constants. So for this given m and k, you can define a curve. The heights are associated with a curve in one-dimensional, a curve, just like a Koch curve or whatever it is. And then you calculate all these lengths and then take the average value of this length for all values of k. So that is nothing but the sum over all these LMs divided by k. So that is LK, which you define as k power minus df. df is nothing but fractal dimension. So once you have fractal dimension, then you can check the other compare with other electrochemical properties. You can also find other interesting exponent, the so-called Hurst exponent, which again tells it's always less than 1, and whether it's less than 0.5 or greater than 0.5 and equal to 0.5, it's Brownian motion type random walk. Less than 0.5, it's persistence or anti-persistence and so on. So you can associate other statistical properties once you know DF and so on. So this is what Higuchi algorithm can be utilized for surface morphology. Now I'm showing this specific measurements of and results of Pandey's group. This paper, for example, Kavyasri, Yadav, Shama, Parveen, Joshi, Leela, Pradhan, and Pandey in Material Research Bulletin in 2019. So you can see some of these pictures, and also Kavyasri's PhD thesis and so on. So there are 4 figures in this ABCD. The first figure is this SEM micrograph of the pristine pure strontium hydroxide deposited onto stainless steel substrate using Szilard technique. Okay. So what do you see? It's a tuberous morphology. You will see the bulbous morphology. You see the same picture shows clearly this tuberous morphology. And then, as I pointed out, you measure the heights of, you divide this into n square pixels and measure the heights of each of these, at each of these pixels, the surface heights, and then you calculate this length, like the one I pointed out from the various height measurements. And the differences between different pixels. And a curve can be identified, a fractal curve, and whose length at each of the segments you identify. And from that, you plot log K versus log LK, and you find the various points fall on a straight line. And the slope of which is nothing but the fractal dimension. So for this pure pristine strontium hydroxide, It turns out to be 1.503 plus or minus something like that, showing clearly the fractal structure. And if you consider the fractal of each of this column of these pixels, so there are 700 pixels that are measured here. So you see that it oscillates between these fractional values dramatically, and this is averaged out, and you get these values. This is Hurst exponent, which is again oscillates between the values 0.4 and 0.5 or something like that. So which clearly show the fractal character of this strontium hydroxide. And very quickly, I will show, I don't know how clearly you see this. This is some images of strontium hydroxide at 1%, 2%, 3% doped copper ions, okay, which show increasing fractal dimension and decreasing Hurst exponent, indicating that the roughness has increased. So you can calculate the fractal structure for each of these three figures and ensure that this fractal structure is preserved. And more doping, I think it becomes more rough and perhaps supercapacitive properties increase. And as you see in this last column, so you have fractal dimension, you have Hurst exponent, and specific capacity. So at 3%, you have the highest specific capacity from the measurements, and for the middle one at 2%, you have 554, and at 1%, you have 467, showing that increased fractal nature also shows the corresponding films show increased electrochemical properties, so on. So confirming that fractal analysis could be a very useful measure of identifying appropriate supercapacitor materials. So again, similar picture for fractal analysis of iron doped strontium hydroxide, again for three percentages of iron doped, FS1, FS2, FS3. And again, they show similar properties. And the last one is yttrium doped. Again, you have similar properties for four types of doped yttrium strontium hydroxide. So they have calculated the corresponding fractal dimension, Hurst exponent, specific capacity, and so on. So all these results confirm that fractal dimension could be a very useful measure to study the morphological properties of supercapacitive materials. And for other thin films also, I think for other nano materials also, fractal study could be quite useful. A question might also arise how the dynamics could be related to these materials, because these fractal dynamics we have already seen in the case of Duffing oscillator and all, they are related to the chaos properties. So can one relate these properties to these systems? I've already pointed in one of the earlier PPTs that some people have identified, for example, Duffing type oscillators with certain nano electromechanical materials, nano films. Again, deposited like this, but at the nano level. So probably these fractal studies could also allow people to look into the underlying dynamics associated with these materials. So that could also yield much more information about this kind of supercapacitive materials. So then to conclude, so what I have tried to point out is nonlinear dynamics is an evolving science. Many new concepts continue to emerge, and I have pointed out one specific area of aspect of this nonlinear dynamics. And these dynamical systems show, particularly when they exhibit chaotic behavior, fractal structure. And these fractals are very interesting entities showing self-similar behavior. And they have considerable significance in the study of surface morphology of supercapacitors. So nonlinear dynamics of these materials are fascinating topics for further study. I do hope that some of the all the participants will find some useful information from the points I have tried to present and use in your further research and studies, and also pass on some of this information to your students in your courses. And here is some general references for the materials I have tried to point out. A general reference for nonlinear dynamics, a book by myself and Rajshekhar, and then on fractals, Fred Jens, Springer, and Michael Barnsley, Fractals Everywhere, academic Dinesh Kumar, Arjunan, and Ali Ahmad, Fractals Application in Biological Signaling and Image Processing, and so on. So with this, I think I have come to the end of my lecture. I have taken almost 2 hours, more than 2 hours. I'm sorry that I have exceeded the time that was given to me. I thought I can finish by 1 hour 45 minutes, but it had crossed the time allotted to me. But I do hope that it was useful to the participants. And perhaps it's slightly different from the earlier talks, which were concentrated more on the experimental and physical properties of energy storage materials. But here I have tried to deviate from that perspective. I had tried to bring in dynamics aspects and try to relate the dynamics with fractals, and then fractals with the study of morphological properties of supercapacitors, as studied by Professor S.N. Pandey and his group. Thank you very much for your attention. If you have any questions, comments, etc., I will be happy to answer them.
Now this session is, thank you very much, sir, for this very nice presentation. Really, that we have enjoyed it. Yeah. So now the session is open for the discussion or the questions. If you are having any, participants probably very much tired because this is the last lecture. Anyone that any query?
Thank you, sir, for this informative talk. Sir, I want to know, is there any intuitive or easy way to define connection between non-integrability and chaos?
Yeah. So that's technical. Yes, non-integrability and chaos. There are connections, but
I think the connection is lost.
Maybe.
Not always mean chaos, but sorry, somebody interrupted my discussion. Yeah, so non-integrability need not mean chaos, but chaotic behavior always implies non-integrability. Okay, so this is a finer distinction. Okay, if you look into my discussion on Duffing oscillator, so in the bifurcation diagram, you see as the control parameter f increases, there are regions where you see period 1, period 2, period 4, etc., etc. So in all those cases, the system exhibits very regular behavior. Okay. But only when you come to chaotic dynamical state, I mean, it shows complex behavior. So you may have systems which may exhibit regular behavior, but still it may be non-integrable. Okay. But on the other hand, when you have a system which is chaotic, you are sure that the underlying system is always non-integrable. So non-integrable systems need not be chaotic. Okay. As I have pointed out, for appropriate control parameters, the system can exhibit regular behavior. Okay. But chaotic systems, which are highly non-linear, which are non-linear, which exhibits very complex motion, and they will exhibit non-integrability property. So is that clear what the answer for the question you have asked?
Yes, sir. I got the idea, and I have similar confusion in this periodicity of orbits and chaos. I mean, if a orbit is aperiodic, is it chaotic as well?
Can you repeat the last sentence?
Like if a orbit is not periodic, can we say it is chaotic?
No, periodicity is one property. Chaos comes in when it shows sensitive dependence on initial conditions and self-similarity. Okay. So non-periodic nature need not imply sensitive dependence on initial conditions. Okay. So this is a very technical point. You should be very careful.
Right, but like I'm thinking in this way that if phase space is bounded and orbit is not periodic, it means that it will never ever come back to its previous point.
Yeah, the phase space is bounded, but within that you can have periodic behavior, you can even have aperiodic behavior, but it need not show sensitive dependence on initial conditions. So that you should ensure. Okay. Then only you can say this is chaotic. Is that okay?
Yes, I got the idea.
Yeah.
Any other question from other participants? No, actually, sir has given very good idea that how we can use the concept of the nonlinear dynamics and factor dynamics to the supercapacitor and thin films and related area. In India, I think that very few groups are working in this direction. So that is the very open field, and one can, this is the appropriate time to enter in this field and to have the idea about the nonlinearity. And probably this theoretical prediction that will be giving more idea that how the thin film should be grown and how the characteristic that should be controlled on the basis of this theoretical study. So in a very simple way, these are very complicated ideas sir has explained. So let us sir, on my own behalf and on behalf of all the participants, I thank you very much for this excellent presentation, sir.
Thank you. Thank you very much.
Sir, thank you.
Okay, goodbye. Okay. I will leave now.
Yeah. Sir. So now the session is open here for the general discussions. So many participants, they have submitted the assignment and the number is increasing on my Yahoo account. So please try to submit as per the time schedule today by 8 p.m. The local participants, they have submitted the physically here. For example, Dr. Ravi Prakash and others, they have submitted it in my office. So that I have obtained that one. So tomorrow I am planning that if you see, The first session, that is your yoga and stress management. Second one is my lecture, and after that I think that I should reduce the time of the lecture. Just I should stop here, and we can